Thank you, Marietta. Good afternoon, everyone, or good morning, or indeed good evening, depending on where you're joining us from. I've been with NEL quite a number of years, joined in 1983, worked on a range of topics over that time, but one of the key things linking all of them has been the need to understand the physical properties of fluids. And in that context, therefore, density is very important. As I hope we will see by the end of the webinar, it is the other vital bit for flow measurement. Okay, so I'll say a brief introduction to the topic, and then we'll have a look at some density measurement techniques. Then we'll look at some calculation methods that you can use for calculating density at different conditions, summarize that lot, and then, as Marietta said, hopefully at the end we'll have some time for some questions and answers. Okay, so why is density important? Well, many process applications, you use density for process control, but also for product quality assessment. And of course, accurate flow measurement is vital throughout process industry. Depending on the technology used, of course, you might be measuring your flow rate by mass or by volume, but there's often a requirement to convert between these quantities. To do so requires a knowledge of density, and a knowledge of density as a function of temperature and pressure. So density therefore becomes a fundamental part of a flow measurement system. A good place to start is by saying, okay, what is density? Density is mass per unit volume. So nice, simple little equation here. And of course, in the SI system, the International System of Units, the unit of density, therefore, is going to be the kilogram per cubic meter. So that's really the basis of density. There are, of course, a number of other ways of defining density. You can think in terms of relative density or specific gravity, which is a density divided by a density of a reference. And the reference has to be at stated conditions. You also have to state what the reference is. It's typically water at 1.01325 bar and 4 degrees Celsius. It might be air if you're talking of a gas, again at the same pressure, but possibly at 0 Celsius. There again, it could be at 15 Celsius, or it could be at 20 Celsius. And it's important to note that a relative density is not a density ratio. A density ratio is the ratio of the density of the fluid you're interested in at a given temperature and pressure to the density of the same fluid at defined reference temperature and pressure conditions. There are other types of densities around. Proof is used particularly in the alcoholic drinks industry, API gravity in the oil industry, and there are, of course, equations for converting between the various units of density. So, for example, API gravity can be related to specific gravity by the equation on the bottom left here, and then, of course, from specific gravity, you can get to absolute density from the equation on the top right. So, that's fine. We now know what density is and some of the ways in which it's defined. Let's take some time now to have a look at how you would actually go about measuring density. And I'm going to split them into two categories, what I've called here offline methods and online or inline methods. I'm also going to touch on the issue of the calibration of the online or inline devices in particular because of their relevance in the oil and gas industry, but also in process sectors as well. So let's have a look at these in turn. How do we determine density? Well, let's take a step back and think in terms of flow rate. What would be a primary standard for flow rate measurement? Bucket and stopwatch. It's about as simple as it gets, plus scales and a ruler, I guess. And of course, you can do that gravimetrically, where you weigh the bucket before and after you fill it, measure the time, or volumetrically, where you measure the change in the volume of the bucket, and you measure the time of the flow. By analogy, density can be measured in a similar way, gravimetrically, bucket and scales and ruler. in principle, determining density of a fluid is simple. Remember, the unit of density is kilogram per cubic meter, so if we weigh a quantity of fluid and we know the volume, we can calculate the density. In practice, of course, even like flow rate, it's not that simple. And we don't tend to do it that directly. There are a range of techniques, and we'll look at each of these in turn. So I'm going to cover hydrostatic techniques, pyknometers, oscillatory techniques, and then just touch on compression and sonic techniques. Hydrostatic techniques are fairly fundamental and consist of determining the apparent weight of a body of known mass and density when it's totally submerged in a test fluid. And we're making use of Archimedes' principle, the buoyant upthrust on the body being proportional to the displaced fluid. Can break that down a bit further into how the systems actually operate. Is that body that's in the fluid connected by a wire to the balance, so it's a mechanical suspension system? Is it connected via some sort of magnetic coupling system? Or a variant of that is a magnetic float system where the body is actually held in equilibrium by a magnetic field. What would that look like? Here's an example of an electromagnetically coupled hydrostatic weighing system. So we have the sinker, the body of known mass and density, immersed in the fluid whose density we are wanting to determine, and an electromagnetic coupling system transfers the apparent weight of the body through the wall of the container to a balance where we can weigh it. So if we know the true mass, m sub s, we measure the apparent weight of the body in the fluid, m sub s star, and we know the volume, we can calculate the density. Again, it looks simple. In practice, there's a lot more to doing that to get a good result, but the principle is simple. And hydrostatic weighing techniques have a number of advantages. In particular, they can be automated. They can also be used over a wide temperature and pressure range, particularly if you use something like an electromagnetic coupling system. They are very accurate, potentially 0.005% or possibly better to 0.02% across extended temperature and pressure ranges. And they're essentially a primary standard method. Plus, they can be used for both gases and liquids. However, as with any measurement technique, there are disadvantages, and careful design and operation is required, particularly if you're going to try and reach those sub 0.01% uncertainties. If they're not automated, they're time-consuming to use, but conversely, automating them tends to make them expensive. The other thing is they're not suited for online use, so they're not process instruments. They are laboratory, primary standard type instruments. Pyknometers, on the other hand, again, are a fairly fundamental technique where you measure the mass of a known volume of fluid. And again, there are a number of variants of that. Capillary stoppered pyknometers, where you compare masses of equal volumes of the sample and a reference fluid, usually water, because we know the density of water very accurately. Graduated bicapillary pyknometers are calibrated using water for precisely the same reason. And you can adapt the technique so that it can be used at elevated pressure. Again, typically calibrating the pyknometer with water. So what do these pyknometers look like? On the left, we've got the capillary stoppered pyknometer, and you can see the fine capillary in the stopper there. The reason for that is that you want to be able to fill the vessel consistently to a known volume, having determined that volume by calibration with water. The capillary stopper allows you to do that because when you overfill the vessel, then put the capillary stopper in, it flows back out to the top of the capillary, and you have a known volume consistently every time. You measure the weight of the empty vessel, then the weight with the fluid whose density you are determining. You've calibrated the volume with water, you've got a mass, a volume, you've got a density. Graduated bicapillary pyknometer and pressure pyknometer, same principles. you determine the volume using the reference fluid, typically water, and then you measure the weight that you have filled and empty. So, simple technique, therefore, and also fairly fundamental. Because it's simple, it's cheap to purchase, and you can achieve good to fairly high accuracy, potentially as good as 0.01%, or typically 0.2%. Depending on the design, they can be used for gases and liquids. The capillary stoppers and bicapillary obviously are liquid only, but pressure picnometers can be applied to gases. Disadvantages, again, careful design and operation are required. They are time-consuming if not automated. They can be automated, but it's fairly difficult and therefore expensive. And again, they're not suitable for online use. Pressure picnometers are really sampling because you're then making the measurement offline. It's not an online measurement technique. So that brings us to what can we use online or inline. And one of the ways of doing that is to measure the oscillation period of a body. And you can do that using a vibrating tube, where you measure the oscillating period of a tube filled with the fluid, or by measuring the oscillation period of a rod or a tuning fork immersed in the fluid. Again, both fairly fundamental techniques. So at the top, we see an example of an insertion densitometer where it's inserted directly into the fluid or sometimes in a side stream, and that would typically be a tuning fork design or a thin-walled cylinder. Laboratory densitometers typically are based on an oscillating U-tube design, and these are offline instruments. They can be used inline, but they're more typically offline instruments. There are other variants, of course. Flow-through vibrating tube densitometers are widely used, particularly in the upstream oil sector. And of course, more recently, Coriolis meters have the ability to measure fluid density as well as flow rate. But again, it's the transverse oscillation that's used there to measure the density. Oscillatory techniques have a number of advantages. They are simple and they are easily automated. They can be used over wide temperature and pressure ranges. They can be used inline, certainly. Many examples are available commercially, and potentially they are very accurate, possibly 0.05, possibly better. Some of the more recent designs are better than that. Again, they can be used for gases and liquids. But then, like all precision instruments, they tend to be expensive to purchase, particularly for the highest accuracy performance. But a key point, as with any of the other techniques, but particularly here where we're talking of online process instruments, is that careful calibration is required. And I'll just briefly mention the other two techniques I had on the introductory slide, which are compression techniques and sonic techniques. Again, a number of variants of compression techniques. We can measure the change in length of a fluid. That could be done using capillary rise, i.e. the change in height of a liquid in a capillary tube as you change temperature or pressure. You can measure the displacement of a piston in contact with the fluid in a pressure vessel, or you could seal the fluid into a bellows and measure the change in length of the sealed bellows as you compress the bellows or expand it. These techniques, of course, are really only suitable for liquids, but they can be used across wide temperature and pressure ranges. Sonic techniques, a couple of variants there. You can measure the speed of sound in the fluid using an interferometer with a variable path length, and you detect the impedance in a vibrating piezoelectric crystal. Or you can use an optical diffraction technique where you measure the diffraction of a light beam through the periodic density variations caused by the sound waves. These techniques have the advantage they can be used for gases and liquids. And again, they can be automated. So, we've seen a range of techniques which are available for measuring densities for both liquids and gases. online, some of them suitable for online use, some only suitable for offline or laboratory use. In general, oscillatory techniques are useful for pretty much everything, general laboratory applications and process applications. But when thinking about what techniques to use for particular application, remember that whilst a requirement for high accuracy or low uncertainty will generally imply high cost, just because you can tolerate a lower uncertainty or higher uncertainty or lower accuracy doesn't necessarily mean that you will be able to use a low-cost technique. I mentioned a few times throughout there the importance of calibration, in particular the importance of calibration for online or inline devices if they are forming part of a measurement system, particularly a fiscal measurement system in the oil and gas sector, for example. Because, as I said at the outset, effectively, density has become a fundamental part of your flow measurement system. So if you are required to calibrate your flow instrumentation regularly, then recalibration of the density measurement system will also be required. And that is a vital part of maintaining your traceability. Calibration is often driven by regulations, and the other key point is that calibration must be fit for purpose. Let's have a look at that. I'm illustrating it from the UK context here, but the guidelines for many other oil and gas producing nations are very similar with regard to calibration requirements, calibration intervals. The UK regulatory position for liquid density measurement, for liquid measurement systems, is stated here and has a requirement that the measurement system has an uncertainty of plus or minus 0.25% of dry mass for quantities exported into common transportation systems, pipelines, shared pipelines. That's from the most recent Oil and Gas Authority guidance notes. Most of the measurement systems in the North Sea still make use of volumetric flow meters. Newer systems are Coriolis-based, and some of the older ones have been retrofitted, but volumetric flow measurement, turbine flow meters, are still widely used in the North Sea and indeed in many other parts of the world. But the allocation is by mass in shared transportation systems, so as we saw, density is therefore required to convert from volume to mass. And the most common instrument used for that is a flow-through vibrating tube densitometer. So given everything I've said previously, it requires the same care in its traceable calibration as the flow meters in the measurement system do. And that brings us to the second point I made there about the calibration having to be fit for purpose. The previous approach within the UK was that the densitometer was initially calibrated at ambient conditions, 20 degrees Celsius, 1 bar, and then corrections were derived for the use at temperatures other than 20 Celsius at 1 bar and for use at other pressures, but these were only derived at 20 Celsius. And typically the annual recalibration was only done at 20 Celsius and 1 bar. But of course densitometers are used at non-ambient conditions, and furthermore the equations which convert the raw signal from a densitometer, the oscillatory period, to density are cross-coupled in that period, the temperature and pressure of the fluid and the densitometer. So recalibrating it at 20 Celsius and 1 bar probably isn't fit for purpose. And as a result of a joint industry project which NEL led on behalf of the Oil and Gas Authority, well, the predecessor, in fact, we came to the conclusion that densitometers should be calibrated at their anticipated operating conditions, i.e. simultaneously at temperature and pressure. And that's now embedded in the OGA guidance notes. So, how do you calibrate a densitometer? Well, use fluids of accurately known density. So the fluids have to cover the full operating density range of the device. They should cover the full range of other relevant properties, viscosity, speed of sound. So the properties must be known across the full temperature and pressure range of the device, because the fluids, therefore, are acting as your transfer standards. And what we did when we started the joint industry project, we had a look, we asked the sponsors, so what range of conditions do your densitometers actually see in service in terms of, let's say, density and viscosity? And you can see there's an outer box full range covering from just over 500 kilogram per cubic meter up to just under 1200 kilogram per cubic meter, and viscosities from 1 up to 40 odd centipoise. And that's for the UK. So that's down to condensate and up to heavy oil. Most common range, obviously, for typical North Sea crudes is in the 700 to 850 kilogram per cubic meter range and below 10 centipoise. And also, I've marked on the graph some fluids which could potentially be used as transfer standard fluids, trying to bracket that most commonly required range. Okay, how do we get the densities of those reference fluids? Well, we have a primary standard densitometer here at NEL. It's a single sinker magnetic suspension densitometer using Archimedes' principle, which I described earlier. It's capable of achieving an expanded uncertainty of better than 0.015% across the temperature range from -40 to plus 150 Celsius at pressures up to 300 bar. Across sub-ranges, the uncertainty is actually lower. We can get down to about 0.007, 0.008% in some cases. That's what it looks like. We've already seen the inner part of that before when we looked at the techniques. So we can see in the middle there the sinker, the body of known mass and density immersed in the fluid, inside a pressure vessel, inside a thermostat. So we can control the temperature and pressure of the fluid whose density we want to measure. The electromagnetic coupling system transmits the upthrust, the buoyant upthrust of the body through to the balance, and we can measure the apparent weight of the sinker and hence calculate the density of the fluid. How good is the technique? Well, it's very reproducible. Here's an example of data from it. 3 sets of data for the one fluid, toluene happens to be, and made over a period from August 2007 to September 2008, 3 sets of measurements, 3 different samples of fluid, 3, as it happens, slightly different configurations of the primary densitometer. And I've just taken the data at 20 and 100 Celsius here, but you can see that the agreement between the 3 sets of data is always within about plus or minus 0.004%. So very, very good reproducibility. That's fine, but how does it compare with literature data? Because we could have a systematic error in there. So here I've compared our data with 2 other sets of data from other national standards laboratories, from PTB in Germany and from NIST in the US. And you can see the agreement with the PTB data is within 0.005%. The NIST data appears to be a bit further off. It's getting towards the limit of what we would think of for our uncertainty. But when I looked at the NIST data in a wee bit more detail, what I realized was that the equation they had quoted was for what they call their standard reference material. And I found a paper which went into that in more detail, where they also had data for degassed and air-saturated samples. Now, the samples we were using, and also the PTB samples that I showed on the previous graph, were degassed. And you can see here, if I look at the comparison to the NIST degassed samples, the agreement is actually much better. It's only at the highest temperature, in fact, that we're much over the 0.01%. So, all in all, we've got good agreement with literature data, so we're confident that we can get low uncertainties in our reference fluid densities. So, how do we calibrate a densitometer? Fill it with one or more of those fluids whose density we now know accurately. Control the fluid temperature and pressure. Temperature stability better than 50 millikelvin. In practice, we get better than that. Pressure stability better than 100 millibar. And then measure the fluid temperature, pressure, and the densitometer output period. Typically, you'll be looking for uncertainty in the temperature measurement of 15 millikelvin. Uncertainty in pressure measurement of about 20 millibar. Period measurement, nanosecond, is easily achievable. What does it look like in practice? Well, here's an example. On the left, in the photo, you can see a typical flow-through industrial densitometer mounted inside the enclosure. The enclosure allows us to control the temperature of the air around the densitometer during calibration, and we can control the temperature of the fluid circulating through the densitometer. Thank you. So we can control both the air temperature and the fluid temperature, and we need to do that because to achieve the uncertainties I mentioned in the previous slide on temperature, and in particular, if we had a temperature difference of more than about half a degree between the fluid inside the densitometer and the air around it, we wouldn't achieve that temperature stability. Hence the need to control both the air and the fluid temperature. What does that get us? Well, here's a snapshot from the uncertainty budget for the facility, and you can see for particular conditions I'm looking at here, 90 Celsius, 91 bar absolute pressure, reference fluid of water. The uncertainty in the calculated density at those conditions is 0.008%. So, we've got a good uncertainty on the reference fluid density there, and a very low uncertainty on the densitometer period. So we can get a very good calibration of the densitometer as a result. In terms of results to date, we've calibrated about 600 of the most commonly used densitometers in accordance with these current OGA guidelines. And we've covered a wide range of conditions from 5 to 95 Celsius and from 5 bar up to 131 bar. Interestingly, about half of the densitometers had as-found errors of between -0.1 and +0.1%, so just about within what you would expect. But the use of average errors actually masks the scale of the problem, because if you break it down by negative errors and positive errors, about 15% had negative errors of more than 0.1% or -0.1%, but almost half had positive errors of over 0.1%, so a significant number of units were overreading. There is no clear correlation between the as-found error and the operating conditions, temperature or pressure. So you can get positive or negative errors with either high temperatures or low temperature, or high pressure or low temperature operating conditions. And if you just try to adjust the base coefficients in the equation, as was done with the previous calibration method, that would still leave about 40% of the units with residual errors of over 0.1%, so you wouldn't have improved anything by the calibration. Optimizing all the coefficients over a limited temperature and pressure range, plus or minus 5 Celsius, plus or minus 5 bar, for example, gives you residual errors of down at the 0.03, 0.02%. And that plus or minus 5 degree, plus or minus 5 bar is representative of the operating condition of most densitometers. Some operate over wider conditions and you would calibrate them accordingly, but typically you'll be in that sort of range. So it's worth thinking, that's fine. As with any instrument, you send it off to a lab, it comes back with a calibration certificate with a nice low uncertainty, but what happens when you put it into use? There are other potential sources of error, and thinking in terms of liquid density, obvious ones are non-representative samples. If the densitometer is positioned somewhere where it's not getting a representative sample from the main flow line. Inhomogeneity of sample in the sensor. If you've got two liquid phases, for example, oil and water not homogenized, then that may cause problems. Solid deposition on the sensor elements will obviously cause problems by altering the oscillatory mass. Solid can also remove mass in the case of sand eroding the surface, and we've seen examples of both of those on units coming to us. Obviously, if you get gas breakout in a liquid system, it's going to give you errors. And stress effects, these are oscillatory devices, but they are mounted into pipework and obviously may be subject to stress at installation or subsequently in use. And one other thing to be aware of course, is that if you have temperature and pressure differences between the densitometer and the flow meter, you need to account for them, particularly if they're more than a few degrees or more than a few bar. Okay, let's have a look at calculation methods, because that sort of feeds on from what I was saying there about the difference in the conditions between the densitometer and the flow meter. But there's a broader picture to that. And thinking in the oil and petroleum products sector in particular, crude oil and petroleum products are typically sold by volume at reference conditions. Those reference conditions may be 60 Fahrenheit, 0 psi gauge, or 15 Celsius and 101.325 kilopascal. You know, we think in terms of the price of a barrel of crude oil. Brent crude is trading at, or West Texas Intermediate crude is trading at $75 a barrel. So we need to know the effects of temperature and pressure on the fluid density, the volume, to convert from the measured conditions to those reference conditions. And this is typically done using volume correction factors, the most widely used of which are those developed and supported and maintained by the American Petroleum Institute. The API volume correction factors have a fairly strong history, fairly strong pedigree. The first widely used ones were the 1952 Blue Book tables. These were then updated in the 1980s with the 1980 tables, and the most recent are the 204 Chapter 11 standard versions. The 1952 Blue Book tables are called the Blue Book tables because they were published in blue bindings, and this is an example of one we have in our library here at NEL. They were jointly published by the ASTM, American Society for Testing Materials, and the UK Institute of Petroleum. But although they were published in 1952, they were largely based on volumetric data for crudes and fractions which were published in 1916, and most of those samples were primarily from UK domestic production at that time. So the 1980 tables were updated. They had better base data and better data handling than the 1952 tables, better base data in terms of covering about almost a third of worldwide production and similar quantity of the estimated reserves from 1974. And better data handling in particular, where the printed tables were replaced with mathematical equations and statistical checks were also used to assess the quality of the data. The 2004 volume correction standard, the Chapter 11 from the API publication, again jointly with ASTM and the Institute of Petroleum, moved away from the printed tables to algorithms only, extending the temperature and density ranges and allowing for combined temperature and pressure corrections. But I'm going to take a look at the use of these combined temperature and pressure corrections, the CPTLs as they're called, to provers, because they're often used to account for the effect of changes in fluid density between conditions at a reference device, a prover, and a device under test, the flow meter. Now, in practice, temperature and pressure differences between a prover and a device under test should be small, so the density corrections will be small, and therefore the potential errors will be small. And that's fine if you're using a prover, which is a volumetric device, to prove, test a volumetric flow meter. However, what about converting to mass? And the reason that's of interest to us is that one of our facilities here, our elevated pressure and temperature loop, uses a compact prover, a volumetric device, as its reference, but typically it is calibrating mass-based flow meters, Coriolis flow meters. So we need to convert density, we need density to convert from volume to mass. In terms of applying these correction factors, in this instance, we're interested in the mass of fluid flowing through the device under test, and it's related to the base prover volume, the BPV, by this equation, which has a number of correction terms. There are correction terms for the effect of temperature and pressure on the volume of the prover, and then the correction terms for the effects of temperature and pressure on the fluid volume. So that's the relationship that we have, and the CPTLs are those API Chapter 11 corrections. So we can express those in terms of fluid densities, and in the API tables and algorithms, the correction terms are split out into temperature corrections and pressure corrections. Temperature corrections are in terms of thermal expansion from a base temperature, and the pressure terms are in terms of a compressibility coefficient. And these have been correlated. They are correlated in terms of a base density at 60 Fahrenheit and 0 psi gauge. Now, interestingly, there is one set of coefficients for the compressibility of all the fluids, but there are several sets for the thermal expansion depending on the liquid's classification and its density at 60 Fahrenheit. And the API splits those into three categories: crude oils, refined products, and lubricating oils. There's an additional special applications category for use when none of the above fit, basically. But to use it, you actually need to determine experimentally the thermal expansion coefficient of your fluid. How good are they? Well, let's have a look. I've taken an example here of one of the oils that we've used in our EPAT facility, and used the API calculations treating it as a generalized crude oil. And at 20 Celsius, it's not too bad. As you move away from 20 Celsius, the errors become quite significant. So at 75 bar, you can see that our errors are anywhere between -0.5 and -0.7%. Well, that's probably a bit unfair. After all, that oil isn't a generalized crude oil. Let's treat it as a refined product, which of course is what it is. 20 Celsius, still not too bad, but 50 and 70, still not good. And EPAT can operate up to 80 Celsius, so those results wouldn't be good enough, as we need density to the order of 0.03%, not 0.3%. Treat it as a special application. Well, we measured the density to determine the compressibility, thermal expansion, sorry. So it's better, but it's still not good enough because EPAT can operate up to 100 bar. So again, we would have an error of 0.1% in density, whereas we're aiming for 0.03%. Not surprising, really, when you dig behind it, because these factors were derived for experimental data only up to 49 bar. The errors were claimed to be 0.1% up to that, which they look as if they are, but undefined above. And so what do we do beyond those conditions? Can we do better? Well, if we rewrite the equation relating the base prover volume to the mass passing through the device under test just in terms of densities, we end up with this equation. So if we can find a better density equation, then we may be able to do better. And we can. We measure the density across a range of conditions, typically from 10 to 100 Celsius and up to suitably high pressure. And we can achieve an uncertainty of 0.025% on direct density measurement. Fit it to an equation of this form, and then we can calculate the density at any condition in that range with an uncertainty of 0.03%. So we've reached our target. That's okay, but you need a lot of data to generate the coefficients for that form of equation, and the coefficients are fluid specific. So this method isn't an API, compressibility correction replacement. But for our application, where density is so fundamental, we have to go down this route. But more generally, be aware of the limitations of the API method if your fluids are non-standard. So to summarize, for liquid calculation methods, the API volume correction factors are widely used for converting from density or volume from measured to reference conditions or vice versa. They are fit-ish for their original purpose, but not necessarily if you're using them as part of a primary reference system. Lower uncertainty can be achieved by using alternative approaches, but they are more application specific. Nevertheless, it's worth reviewing the general application of your calculation methods. That's liquids. Just briefly, I'll touch on gases. For pure components or certain mixtures, for example, pipeline quality natural gas, the easiest and most accurate method of determining the density is actually just to measure temperature and pressure and calculate it using an appropriate equation of state. For pure components, you use packages such as NEL's PPDS package or the US Bureau NIST package RevProp, and they'll typically give you uncertainties of anywhere between 0.02 and 0.05% for gas phase density. For natural gas mixtures, the most widely used are the AGA-8 and the GERG 2008 packages. They'll give you uncertainties of between 0.1 and 0.5%. For mixtures, of course, you need to know the composition to use an equation of state, and that could be measured online using a gas chromatograph system, for example, or by taking samples and analyzing offline, again, potentially with a chromat system. But if what you do if the composition isn't known, or in fact it's outside the limits for the equations, particularly for the AGA-8 or GERG equations, well, you can measure it using online densitometers, and we touched on some of the techniques earlier which could be used for online gas density measurement. In particular, the oscillatory densitometers, the insertion type densitometers, are ideal for that. But again, you have to be aware of potential errors, and so in the potential errors I have included calculation because, as I said in the previous slide, for pure components or for mixtures of defined composition, then the calculation approach is the most accurate, but you have to sample, so you have to be sure you're getting representative samples, and you have to make sure you're using an appropriate equation of state. For direct measurement techniques, potential errors include, obviously, similar to liquid errors, so solid deposition on the sensor element, erosion of the sensor element. You might say, how am I going to get erosion if it's a gas? Well, there could be liquid entrained in there, which can cause erosion. There can be solid in there. We've seen examples of that as well. Liquid in the sensor element obviously will cause mismeasurement. And again, they are oscillatory devices, so stress effects will also be a potential source of error. Again, as for liquid systems, temperature and pressure differences between the densitometer and the flow meter in a flow meter situation should be small. Okay, so let's just summarize what we've looked at. Hopefully, I've demonstrated the importance of density for flow measurement, justifying my title of density being the other vital bit for flow measurement. Flow measurement is vital throughout process industry, and that measurement has to be accurate. But depending on the technique used, you may be measuring volumetric flow or you may be measuring mass flow, and there's often a requirement to convert between those quantities. The conversion is through density, and the density you need to know is a function of temperature and pressure. So density therefore becomes a fundamental part of your flow measurement system. We've seen that there are a number of density measurement techniques available, but that for any of these, as with any measurement technique, appropriate calibration is vital. There are also a range of calculation methods for expressing density at alternate conditions, particularly for liquid applications, both for measurement systems and for calibration applications. But again, it's important that you use the relevant ones. And there are a range of techniques for calculating densities of gases and gas mixtures. Again, it's important to be able to measure the composition if it's a mixture and understand what the limitations are of the various equations of state and which are the best to use for particular applications. Obviously, as well as the measurement of flow rate directly, density as a quantity is often used for process control and for product quality assessment, for deciding where you are in a batch run, for deciding whether that product meets your quality specifications. So overall, density is vital. And just to put that into context here, at NEL, where we maintain the UK National Flow Measurement Facilities, density determination sits at the heart of that. It's used in all the facilities for mass to volume interconversions directly. Down on the bottom left there, we've got EPAT, the Elevated Pressure and Temperature Facility, which I spoke about, where it's used directly in converting from the volume passing through the prover, our primary reference, to mass through the devices under test. In the water flow facility just above that, and in the oil flow facility at the bottom right, it's again used because we have primary gravimetric flow measurement systems and we have secondary volumetric flow measurement systems, so we need density to interconvert. It's similarly used in our multiphase facility and wet gas facility, and will be in the new advanced multiphase facility. In those three facilities, density is also used directly as part of cross-contamination calculations. So the accurate determination of these densities is absolutely fundamental to everything we do in terms of primary flow measurement here at NEL, and that's true for any other flow laboratory worldwide. Okay, so hopefully I have illustrated the importance of density to flow measurement. Thank you.
Okay, thank you for that, Norman. I think we've got time for a couple of questions. So if you could just bear with us just for a couple of moments till we pull up some questions. Sorry, just in the meantime, while we're pulling off the questions, you'll see a list of some forthcoming events where NEL are going to be in attendance. We've got our own organised oil and gas focus group meeting in Aberdeen next week. If you're interested in our next webinar, it takes place on the 26th on CFD erosion modelling. And we're going to be attending a number of oil and gas shows in the coming months, so look out for us there. All the information's on our website as well. If you're going to be along, just would be pleased to see you. Give us a wee shout. So let me just see if there's any questions. Is there a couple there?
Yeah.
Norman,
Okay.
that you want to pick up?
Yeah. There's a few here. Interesting. So, question here asking if we've tested the new Anderson-Hauser ProMass Q density meters. Yes, we have done some tests on them, not as many as the standard 7835s, but we have tested them. And in fact, I think there was a paper at last year's NOFC workshop, or perhaps the year before, with some information on that. So there is some information out there in the public domain on them. Another question here, somebody asking about radiometric techniques for measuring density. It depends on the application. We do use gamma ray densitometers in our existing multi-phase facility for measuring essentially the void fraction across the tube. Now, you can infer density from that, and they can be used, but they're not routinely used, partly because obviously you're handling a radioactive source. Oscillatory densitometers tend to be a cheaper and, if properly calibrated, more reliable way of doing it. So for certain applications, they can be used. They might be useful for things like particularly viscous fluids, or perhaps slurries would be an application where they would be a useful technique to use. Got a couple of others here. Somebody saying, if I'm calibrating a densitometer, do I need to worry about viscosity? Well, I did mention it in the passing, and it really depends on the density measurement technique. For oscillatory densitometers, yes, because oscillatory densitometers are sensitive to viscosity as a second-order effect. The laboratory densitometers that typically use, the Anton Power densitometers, for example, have a viscosity correction built into them. That correction was actually developed by a company in the UK. So density is the primary, viscosity is the secondary, and you can tune oscillatory techniques to be either densitometers or viscometers. So you do need to worry about viscosity when you are thinking about calibrating a densitometer. And that's why we had that range of fluids there covering viscosity ranges. Here's another one. That's quite an interesting one, actually. Somebody asking, this is a gas one. Somebody saying, I'm using a software package for calculating the properties of gas mixtures, and I keep getting these warning messages if I've got hydrogen in the mixture. Should I be using a different package? Well, I'm not going to give a shameless plug for NEL software here, because you'll get the same error messages. The problem isn't you, it's the hydrogen. Hydrogen is a very difficult substance for calculating properties of for equations of state for mixtures. Equations of state are written in terms of reduced variables, which make use of properties of the fluids called the critical properties. And for hydrogen, they're so different from all of the other systems that you end up with numbers which are very different. And when mathematically you try to solve the equation, the mathematics gets quite difficult, and the equation solvers don't tend to work. So systems with hydrogen equations struggle to solve. This is well known, and there's work being done to address that, but it's still an outstanding issue.